Hey guys, my name is Newman Waters. I just wanted to give you a little bit of an overview of universal gates. So the first thing to note is De Morgan's laws. Those are the most important things that we're probably going to be learning, at least in this first chapter. It really says that if you've got a NAND gate or NAND operation, you can convert it into a combination of OR operations. And if you have a NOR operation, you can convert that into some combination of AND operations. And those are the only two laws that really state that you can convert between those two. And that being said, you can then use NOR gates and NAND gates to create all of the fundamental gates, including NOT, OR, and AND. And so I prepared a few examples of how it works. On the left side here, you can see the NOR implementation of the three basic gates, so NOT, OR, and AND, and then the NAND implementation. And so when I click through these things, we'll be able to see both at the same time. So at the top here, the top row of each one, you see the original gate, how it's supposed to work. And the bottom, you can see the implementation using that specified gate. So as you can see, as you'd expect for a NOT gate, nothing's coming in. A is 0, and so the output is 1, or it's inverted, and so you can see the LEDs lit up. But when I click it, you can see that it just inverts these LEDs. They invert whatever my input is. So even with the NOR gate and NAND gate, it's still doing the exact same thing, and you can see that you've just tied the two inputs to the same input to the two different pins. All right, and that's basically how that works. For the OR, the behavior is at least one of them needs to be on for the LED to be on, and you can see here for my OR gate, we've got 2 of these NOR gates, and then we've got 3 NAND gates to do the same exact thing, but you'll see that they all work exactly the same way, even if the actual design of the gates themselves is a little bit different. They work exactly the same way. They'll all light up at the same time. And then for the AND, here's the 2 AND gates. We have 3 NOR gates to build an AND gate and 2 NAND gates to build an AND gate. And you can see you need both of them to be on for the LED to turn on. So one or the other doesn't work, but if you have both on, they'll all turn on. And the reason why we want to cover this stuff is because in the real world, as I've written here, it's sometimes easier and cheaper to manufacture certain types of gates. I think the NAND gate and the NOR gate are relatively simple. And since you can create all of the fundamental gates using either one of these, it's much more beneficial to just mass produce NAND gates or NOR gates and then use those to build up all of the other fundamental gates. Even if you have to use 3 NOR gates for an AND gate, for example, it's still probably easier in terms of economies of scale to just mass produce them, because you're going to get cheaper costs rather than specializing on every single one. And so that's probably the rationale. And then also at the transistor level, certain gates are they use less transistors and therefore less material, and that also reduces the cost. So for example, the NAND gate is used to actually implement a real AND gate. So instead of building a straight up AND gate with transistors, they'll put it in this type of format. They'll use a NAND gate and an inverter to realize just a basic AND gate, because it's actually cheaper to manufacture. Even if it's a little bit unintuitive, that's something that they'll do. And so it's in their benefit and it's in their best interest to understand how to do this conversion. Because let's say you want a company to build your circuit for you, you just send them the design, the logic gate. Well, then they can create any gate for you as long as they know how to do these types of conversions. And so we'll get into how to actually do this. How do we actually derive these different circuits, and then why? And so I'll show you now.
All right, so now that you've seen how they actually work, you've seen that the gates are equivalent, how do we actually derive these things? Because for example, in an exam, we might ask you, here's a circuit made out of AND, OR, and NOT gates. Can you turn them all into NAND gates, or can you turn them all into NOR gates? So I'll show you how to do this. We can just start by showing how to design each individual gate, NOT, AND, and OR, using the 2 universal gates, so the NAND and the NOR. And once you know how to do this, you can literally just one-to-one replace it. So if you see a NOR gate, if you see an OR gate in a circuit, you could just replace it with the equivalent that we're going to design here. So the first thing that we have to do is, like if we want to design a NOT gate out of a NAND gate, we have to decide how does the circuit actually behave. So a NOT gate works like this. A goes in, and then the equation that we get out is going to be the invert of that. So it's going to be not A. Now, our NAND gate obviously has two inputs, A and B, and it has an output of A and B not. Now, we want this to, of course, be A not, this whole side here. So how do we do that? Well, if we, want this to become A not, well, we can just replace B with, instead of putting B, we just put A, and then obviously, using the simplification laws, we can just say that this becomes A not. So what do we have to do? Well, we just have to feed the same input in to both sides of the gate. Both of them are A. And then what we get out on the other side is A not. And you notice these two match perfectly. They do the exact same thing. And so therefore, this is the equivalent of a NOT gate. I'll just circle it here. So this is the equivalent of a NOT gate built out of a NAND gate. For the AND gate, this is pretty easy because it's literally just the opposite of what the NAND gate does. So if we want to get A and B as our behavior, but we only have a gate that can do Y is equal to A and B not, well, let's just take the output of this thing and invert it again. So, let's just add a NOT gate to the end of that. So let's start with our original. And then let's add a NOT gate. So how do we build a NOT gate? Well, we just designed it up here, right? So we just put a NAND gate, two of the same input, and that gives us Y is equal to A, B. I probably should have written it in red. I guess I'll do that. And so this whole circuit here models the AND gate exactly. Even though it uses two gates, we're using the one that we're provided with, and it gives us the exact same behavior. And this is kind of, the universal aspect of it. And turning NAND into NOR is a little bit harder, right? Because we have to start with, the AND here and then get this plus sign. Now, De Morgan's law is really the only way that we can do this because there are, these equivalencies here. So what do we need? We need Y to be A or B, right, for an OR gate. And we start out with a gate that can do this. So we have a gate that can do Y is equal to A and B not. Well, obviously you see that this and this are exactly the same, so we can rewrite it as such. So we'll rewrite it as A not or B not. Now, this is still not what we want because we need it to be A and B. But, one thing you'll notice is if you feed in A not here and you feed in B not here, what are you going to get? I mean, you're just going to get A not or B not, and this gives you A or B, which is kind of what we're looking for, right? Well, I mean, it is what we're looking for. So we need to just do that. So what we can do is we can invert these two inputs up here, and then that will give us our desired output. But of course, to invert, we need to add NOT gates. So we need to add two NOT gates, one here and one here, before it gets into the NAND gate, and then we should be done. So let's do that. So we have A and this. So that's our first NOT gate. And again, it has the exact same behavior as a NOT gate. It just looks a little more complicated. And that's B. So this one here is A not. This one here is B not. And then we're going to feed them into the last NAND gate, which should give us A or B, right? And you can see that these two lines here, or these two wires, are the same as the wires that are here. We've just added a NAND gate before that. So this is how you convert, or this is how you design an OR gate out of NAND gates. And, it's more complicated, but, at least you're only using one. So, use the De Morgan's law to figure this out, and you'll be good to go. We can do the same thing for the NOR, so let's do that. So let's do our NOT gate has this behavior. We've got a gate that can do this, so it should be A or B not. Well, if we have both the inputs again as A, then what we would have is we'd have A or A or A naught, and this is obviously just A naught, so we just feed the two inputs into the same spot, and it should give us the behavior that we expect. So that should be A, and it gives us Y is equal to A naught. So this is the same as the NOT gate, and we're good to go. For the NOR to OR, well, this is again same as NAND to AND. It's very simple. We're just gonna negate the output of the NOR. So A or B, this one gives us Y is equal to A or B naught. So let's just add a NOT gate to the end of this circuit. So we'll do the original NOR gate. So I'm really bad at drawing these things. We'll add a NOT gate to the end. And this should give us a output of A or B, right? Because here this wire is going to be A or B naught, and then this one will, turn it into A or B naught, which is of course just A or B. So this is our OR gate, designed out of NOR gates only. And then finally, NOR to AND, same thing. We need to use De Morgan's. So an AND gate has the behavior A and B. But what do we want, or what do we start with? We start out with A, B, A or B naught. So obviously you can see that this matches De Morgan's law, so we can rewrite it as A naught and B naught. So A naught and B naught. So what happens, what happens now is, oh shoot, what am I doing? Yeah, this should not be here. My bad. It should not be a NAND gate. It should be a normal AND gate. So what happens when we do the same thing like we did before? Well, if we invert these two inputs here, what do we get? We feed in A naught here. We feed in B naught here. It becomes A naught, B naught, which just becomes A, B, or A and B, which is exactly what we're looking for, right? So let's do that. So let's add two NOT gates before this NOR gate. So the NOT gates look like this in NOR format. Same exact thing that you do for the NANDs. And then we'll feed in those inputs into another NOR gate. And then we're good, right? Because this wire here and this wire here, those are the same as these wires. We've just added that inverter such that it comes in as the inverted thing. And then we get Y is equal to AB. And so this is how you would design a AND gate using only NOR gates. And the reason why you want to do this, of course, is as we've mentioned before, in a factory, you want to produce a lot of one thing for the best economies of scale, cheapest production. So you just design a lot of NOR gates or a lot of NAND gates, just one or the other, and then you could design all the other gates. It's better to do that than to specialize and have like 6 production lines for each separate gate. Even if it might be more expensive, for example, 1, 2, 3 gates for just one thing here, well, it still might be cheaper to produce more of these NOR gates because you're doing it at scale, right? And you'll learn a little bit later that the actual design, like the transistor level of some of these gates, some of them use less transistors. And I think that the NAND gate, for example, uses less than to design like a straight up AND gate. So instead of designing, an AND gate just standalone, what you would do is you'd build a NAND gate first and then put a NOT gate at the end. And I think that that's how they do it, just because of the way that, the amount of transistors that are used. So these are the reasons why you need to do it. And, you'll be asked this stuff on the exam. So make sure to practice it. Once you have a circuit that is, we give you a circuit that has AND OR gates, you can just replace them as such. So if you see an AND gate in your circuit, literally just replace it with this whole thing, and that's all you need to know. So you can memorize this, you can derive it. I'd suggest learn it like this first, and then you can memorize it or write it down. You should be good to go.